In a study by Blaisdell and colleagues, rats experienced a flashing light that was sometimes followed by a tone and other times followed by the delivery of a sweet liquid, a common cause model. Then, one group of rats experienced the tone alone, the observed tone group, and one group experienced the tone each time they pressed a lever that had been introduced into the test chamber, the intervened tone group. The rats in the observed tone group often went to search for the sweet liquid after the tone occurred, but the rats in the intervened tone group searched much less often. The authors suggest that the rats had recognized the common cause structure, and those in the observed tone group reasoned that the light had likely occurred, though was missed, and so went to the food source. The rats in the intervened tone group, however, attributed the tone to their actions, and thus did not assume the light had occurred. In contrast, rats in another experiment were presented initially with a causal chain, i.e., a tone was experienced before the light, and the light was experienced before the sweet liquid. In the subsequent test, these rats did not act differently if the tone occurred alone, or if their lever press was paired with the tone. They searched for the food with equal frequencies. Here, it seems that the rats recognized that the occurrence of the tone would lead to the sweet liquid, regardless of their intervention. The rats in this study appeared to be creating predictions about the outcomes of their interventions, lever pressing, after learning about a causal structure purely through observation. This ability undermines most associationist accounts and presents a far more complex view of animal causal cognition than was previously available. Yet, there is reason to question whether what rats are doing is similar to how humans approach such a task. Penn and Povinelli, 2007, point out that humans engage in interventions in a deliberate and strategic manner, often to test their own hypotheses about causal structures, and no evidence exists at this time for this behavior in animals. Further, as will be seen in the next sections, it is still unclear how the causal knowledge observed in studies such as that of Blaisdell and colleagues might be evidenced in other behaviors, such as during tool use. Researcher profile, Dr. Ed Wasserman. As a child, Ed Wasserman surrounded himself with animals. His pets included turtles, frogs, fish, lizards, and a variety of birds. It seems rather unsurprising, then, that he ultimately became one of the most prominent researchers in the field of comparative cognition. Yet, as an undergraduate at the University of California, Los Angeles, he initially majored in physics. After taking a few courses in psychology, though, Wasserman became interested in the study of learning, both in humans and animals. The prospect of scientifically studying behavior, along with its challenges and controversies, was captivating. He switched his major to psychology, and then moved to Indiana University to complete his PhD with Drs. John Jensen, Jim Dinsmore, and Elliot Hurst. In 1972, Wasserman joined the faculty at the University of Iowa and has worked there ever since. During his career, he has studied cognitive evolution by examining the behavior of pigeons, rats, chickens, baboons, and humans. His contributions have been wide-ranging. Indeed, his work has been cited in many different chapters of this book. In the early 1980s, Wasserman began a line of research most relevant to this chapter. His work examining causal reasoning across species has sometimes resulted in findings that do not fit most traditional associative learning theories. In response, he and a collaborator, Linda Van Ham, developed a modified version of the Rescorla-Wagner model that provides an associative account of causal learning. Wasserman's research framework is illustrative of the field of comparative cognition. Naturalistic observation of behavior can be invaluable to generate hypotheses, yet laboratory experiments provide insight into the mechanisms underlying the behavior. His overarching goal is to characterize the basic components of cognition, which he thinks humans and other animals share. Wasserman proposes that even human behaviors that may be species unique, like creating music or complex theories of physics, are the outcome of foundational cognitive processes that are widespread among animals. He has encouraged the growth of the field as a co-founder of the Comparative Cognition Society, a scientific organization. dedicated to the study of cognition across species, and many of his writings discuss the role of comparative cognition within psychology and ethology. Wasserman notes, "My enthusiasm has not waned, and I look forward to further adventures in uncovering the basic laws of learning and cognition. This task will be all the more enjoyable because of the opportunity to work with so many talented students and colleagues." Object physics. Many researchers, particularly in the field of cognitive development, have considered the topic of causality to include the understanding of basic object physics. As Belargian and colleagues state, causality can be construed at a very general level in terms of the construction of conceptual descriptions that capture regularities in the displacements of objects in their interactions with other objects. This construal goes beyond the ideas put forward by ch8, in which one event is recognized to bring about another event through transmission of some type of force, e.g. a launching event. Instead, this broad meaning of causal reasoning considers questions such as, will small objects stop moving after making contact with larger, heavier objects? Can short screens hide tall objects? Can objects suspend in the air without support? Recognition of basic aspects of object physics allows for prediction of, for example, the end state of moving objects. A rolling ball will stop when it hits a solid wall, or the most efficient tool to achieve one's goal. A solid cane will pull in an object, but a flimsy one will not. Studies tapping into the understanding of object physics have a rich history in the study of infant cognitive development, and many of these paradigms have been modified for use with animals. This section will summarize some of the findings across two categories of object features: the movement of occluded objects and solidity support. Object permanence and tracking the displacement of objects. Behaviors such as foraging and hunting often rely on the ability to keep track of objects over space and time, and occlusion. Recognizing that objects exist even when they are out of view or imperceptible via scent or sound implies the concept of object permanence. Some of the work already presented in this book would suggest that some animal species represent the location of objects even after they undergo occlusion. For example, in order to show the ability to perform simple addition and subtraction in the tasks described in Chapter 6, monkeys would have to keep track of 1 to 4 objects that were hidden behind a screen. Other studies have examined object permanence with object displacement tasks. For example, Barth and Kell, 2006, tested chimpanzees, bonobos, gorillas, and orangutans with a task in which a piece of food was hidden under one of 3 opaque cups, and then the cup was moved to another location, i.e. a simplified shell game. To subsequently find the hidden food, the observer must possess object permanence and also recognize that the food moved with the cup, even though the only object observed to move was the cup. In general, the chimpanzees and bonobos performed better than gorillas and orangutans on these tasks, though on other related tasks involving the displacement of objects, all 4 great apes performed similarly. Some research has suggested that ape species may perform better on tasks like this than monkeys, but only a few monkey species have been tested, and in some cases, the performance is actually similar to apes. Outside of the primate order, species such as African gray parrots have also displayed object permanence and the ability to track hidden objects, but bottlenose dolphins have only shown evidence for the former. A question remains, however, as to what cognitive processes underlie this ability. Do animals, for example, understand why the food moves along with the cup, e.g., due to containment within the cup and the contact with the cup's solid sidewall, or do they base decisions on other types of information, such as an association between the cup and food, or an assumption that the two are somehow connected? These tasks alone cannot determine the basis for successfully tracking the food, but other research that more specifically examines animals' understanding of physical features, such as solidity and support, may shed some light on the understanding of the physical world. Solidity and support. In 1992, Spelk and colleagues tested the development of the understanding of solidity in humans, specifically how solidity constrains the path of a moving object. The task was conducted with infants and utilized a looking time methodology, in which longer looking to certain events is assumed to index an infant's recognition of inconsistency or unexpectedness. First, the infants were presented with a solid shelf that had been placed above a solid stage floor, figure 8.4. An occluding screen was then placed in front of the display, and an object was dropped from above the shelf. When the screen was removed, the infants either saw that the object was sitting on the shelf, an outcome consistent with the constraints of solidity, or saw the object on the stage floor under the shelf, an inconsistent outcome. 3- and 4-month-old infants looked longer at the inconsistent event, suggesting some level of understanding of how solidity affects the movement of objects. In contrast, no looking time difference was found in a control condition in which the objects were not seen to drop, and thus the results of the experimental condition were likely not due to a simple visual preference for objects on the stage. Figure 8.4, testing events from Spelk et al. 1992. After observing the ball drop behind the screen, infants would see an outcome that was consistent or inconsistent with the property of solidity. Okay, so you can see a ball dropping from above, dropping behind a screen that has a shelf sticking out on either end of it. And then the consistent result is the ball is now on the shelf when the screen is removed, and the inconsistent result is that the ball is now under the shelf when the screen is removed. In an analogous task with rhesus-macaques, Santos and Hauser 2002 found that the monkeys looked longer when an object was revealed to be under a solid table, as if it had fallen through, than if it appeared to have stopped on the surface. Yet, a different picture emerges when the dependent measure is search behavior instead of looking duration. In the same study, rhesus-macaques erroneously searched for the fallen object under the table. Chimpanzees, orangutans, gorillas, and bonobos made a similar error on this task when searching for the object, though performance improved over test trials. Thus, it seems that both monkey and ape species have some understanding that solidity constrains object motion, but the knowledge is not evidenced in search behavior without experience. However, many researchers have posited that an additional feature of this task, the influence of gravity, may play a role in subjects' incorrect searches. See box 8.2. This proposal is supported by additional experiments showing that performance improves in a horizontal version of the task. Box 8.2, the gravity bias. Often, the verbal, pointing, and reaching errors that participants make on experimental tasks shed light on their underlying cognitive representations. One particularly informative error was observed in a study of children's understanding of the interplay between solidity and gravity. In Hood, 1995, 2-year-old children observed a ball as it was dropped down an S-curved opaque tube and slid into an opaque cup. Of interest was the particular cup, of a possible 3, that children would search to obtain the ball. Children frequently erred by searching directly beneath the point at which the ball was dropped, evidencing a gravity bias. The tendency to search in a straight line path from the release point of the ball was not observed when the apparatus was placed in a horizontal position, suggesting that the bias is specific to vertical motion. Studies using a similar procedure with cotton-top tamarins, common marmosets, and dogs have documented the same pattern of errors. Though results with chimpanzees are mixed, it is possible, then, that instead of basing search behavior on knowledge of how gravity and solidity interact in the bent tube, the human and animal participants were relying on a rule they had formed through experience that objects tend to fall straight down. What remains in question is whether the species tested in this task actually have knowledge of the physical constraints involved, yet cannot override a prepotent, rule-based expectation, or if an understanding of the interplay between solidity and gravity in this event is beyond their ability. One clue comes from a study with young children that replicated the gravity-biased search, yet also found that children looked predictively to the correct location when the ball was dropped. Children may have understood the object physics of the event, yet searched based on a gravity bias. Because the cognitive demands of holding a representation of the occluded ball, producing an answer, and inhibiting the bias were overwhelming. In contrast, predictive gaze required only two of the three demands: representation of the ball's location and inhibition of the gravity bias. Alternatively, children may have only achieved a weak abstraction of object motion regularities that underlie movement in the tube, and this limited understanding perhaps could guide eye gaze but not overt search behavior. Either interpretation is possible for the animal species tested as well, as at least one species, the common marmoset, has also shown looking behavior but not reaching behavior, consistent with a representation of the object's movement in the tube. Additionally, it is possible that some of the species tested do not have knowledge beyond a gravity rule. A more complex understanding would presumably require experience with analogous physical events in their environment, e.g. objects sliding down an inclined plane, etc., and for some species, these events may simply not occur with sufficient regularity. Another way to examine the understanding of support and solidity is to ask whether observers recognize that objects should fall if not adequately supported. For example, Belgeron and colleagues found that during infancy, humans incrementally develop an understanding of support such that at 3 months, any form of contact with a platform is assumed to keep an object from falling, but at 12.5 months, there is a more mature understanding of the importance of the amount and distribution of contact. An analogous study was conducted with juvenile and adult chimpanzees, and results suggested that for this species, it is the amount of contact between the platform and the object, regardless of where the contact is distributed, that determines whether the object should fall. In one of the experiments in this study, for example, the chimpanzees did not increase looking to an event in which the side of the object contacted the side of the platform, yet the bottom was not supported. The authors note that Kohler, 1927, found that some chimpanzees would press a box against a wall and then try to climb onto it to reach food, a seemingly analogous error. It is thus possible that chimpanzees differ from humans by basing judgments of support on simple rules regarding amount of contact rather than a conceptual understanding. However, the authors admit that further studies are needed to rule out other factors, such as assumptions the chimpanzees may have made that the object was stuck to the side of the platform, which it actually was in order to create the effect. Research on the understanding of object physics in animals has primarily been conducted with primates, owing perhaps to the motivation to compare cognitive processes with humans. Other species, such as dogs, dolphins, and some bird genera, however, have also been tested. In some, there is evidence that many animals are sensitive to regularities in the way objects move in relation to environmental features. As noted in the introduction to this section, this is a broad consideration of causality, though attention to the constraints of object physics can lead to predictions regarding the outcome of events. In the next section, the focus will switch to tool use, a behavior for which the physical features of objects and the outcomes of those features play an important role in the efficacy of a tool to cause completion of a goal.